Welcome to the Deep Dive. Today we're looking at some technical work that really challenges a long-standing belief about large language models.
Yeah, the idea that their internal states, the hidden states, must be inherently lossy.
That they compress information, maybe mash different inputs together.
Because you've got all these nonlinear steps, normalization. It just felt like information had to be lost, like different prompts could end up looking the same inside the model.
Making it impossible to know exactly what went in.
Right. But this research we're diving into presents a mathematical proof arguing the opposite.
Saying that standard decoder-only transformers are actually, almost surely, injective.
That's the term, structurally lossless. It means, barring some very specific mathematical exceptions, different inputs create different internal states.
Okay, so our mission today is to unpack that. We'll look at the theory, the math behind injectivity.
And then this algorithm, SipIt, that actually uses this property to perfectly reconstruct the input text from those hidden states.
Let's start with that core idea, injectivity. In the context of an LLM, treating it as a map from the input prompt
A sequence of discrete tokens.
to a sequence of these continuous vectors, the hidden states. What does injective mean for that map?
It means it's one-to-one. So if you take two different prompts, let's call them sevens allow, so neck, ass, lass.
Yeah.
Then their final hidden state representations, low s injectivity, must also be different, low s1, no collisions.
And you mentioned almost surely injective. What does that qualifier mean?
It means this property holds for, well, basically all possible parameter settings of the model. The set of parameters where it doesn't hold is mathematically negligible.
This still feels counterintuitive, though. Things like layer normalization seem like they average things out,
Yeah.
or MLPs squash value.
I know, it seems like they should be lossy.
So why does the math say otherwise? What's the core insight?
It hinges on the mathematical nature of the transformer's components. Everything inside embeddings, layer norm, attention, MLPs, even the residual connections, they're all what mathematicians call real analytic functions.
Okay, real analytic. Let's slow down there. For listeners, what's the key takeaway from calling something real analytic?
Think incredibly smooth. Locally, they behave like polynomials. They're predictable, not jagged or chaotic. They can be described by convergent power series.
And that smoothness, that's the key to preventing information loss.
It is. Because of this property, the points where collisions could happen where different inputs map to the same output form a very special, very thin set in the huge space of all possible model parameters.
Like finding a specific line or surface in a vast multidimensional room.
Exactly. It's a measure zero set. It has no volume, mathematically speaking.
Oh, okay.
And since the parameters are initially chosen randomly from continuous distributions,
Like picking a random point in that room.
the probability of landing exactly on that zero-measure collision set is zero. So collisions are theoretically possible, but practically won't happen. The structure itself avoids them.
So that covers initialization. Random parameters almost certainly give you an injective model. But what about training? We spend ages pushing these parameters around with gradient descent. Does that break injectivity?
That's a critical part of the proof, and the answer is no, it doesn't break it. Training preserves the property.
How?
Because the gradient descent update step itself is also a real analytic map.
The process of updating the weights is smooth too.
That's right. We start with parameters drawn from an absolutely continuous distribution, think Gaussian or uniform, which already avoids the measure zero collision set with probability 1.
Okay.
And since the update rule is real analytic, applying it even thousands or millions of times keeps the distribution of parameters absolutely continuous. It can't suddenly concentrate the probability onto that thin pathological collision set.
So training might move the parameters, but it can't guide them into that tiny fraction of space where collisions occur.
Correct. The property holds almost surely at the start, and it persists throughout training. It's robust across common setups, different initializations, model sizes, even things like mini-batch gradient descent. It's fundamentally structural.
That's a really strong theoretical claim. Okay, so if the model is basically guaranteed to be a perfect memory machine, how do we actually read that memory back? How do we invert the process?
That's where SipIt comes in. Sequential inverse prompt via iterative updates.
And it uses the transformer's own structure, right?
Yes, specifically the causal structure. Remember, in a decoder-only model, the state at position $, only depends on the input tokens up to $t. So $6 to $, plus the current token battery.
Right, it only looks backward.
SipIt leverages that. It reconstructs the input sequentially, one token at a time.
So you figure out the first token, then use that knowledge to figure figure out the second, and so on.
Precisely. At any step, $2, SipIt assumes you've already found the correct prefix, say S on aller and T taft or no.
Okay, you know the story so far.
Then the task becomes, which possible token 5 UJellers from the entire vocabulary of dollars, when added to the prefix pedal, produces the hidden state validity that we actually observed at position dollars?
And because we've established that this one-step mapping from a candidate token Vigeller to the resulting hidden state Ageller given the prefix Vigeller is almost surely injective.
There can only be one token Figeller in the whole vocabulary that correctly produces halite.
A unique match.
Guaranteed. SipIt just needs to test the candidates. It's the first method shown to provide guaranteed exact input recovery.
And it's efficient. What's the complexity?
The guarantee is linear time. Worst-case complexity is SULID v iterations. The dollar is the sequence length, Vigeller is a vocabulary size.
So basically, for each token position, you might, in the worst case, have to check every word in the dictionary. That sounds very manageable.
It is. It turns input recovery from potentially a hard optimization problem into a structured, efficient search with a guarantee.
Okay, the theory is compelling. The algorithm seems practical. But theory is one thing. What about real-world models? Did the researchers actually try to find collisions in big, trained LLMs?
They did. And the empirical results in the sources are quite striking. They ran a huge search for collisions.
Which models did they test?
A pretty wide range. The GPT-2 family, the Gemma 3 models, 1 billion, 4 billion, 12 billion parameters, also Llama 3.1, 8B, and Mistral 7B, so different architectures, different sizes.
Covering a good chunk of modern LLMs. And how extensive was the search?
They compared last token hidden states from 100,000 different input prompts. That resulted in about 5 billion pairwise comparisons.
5 billion pairs. That's thorough. And the outcome?
0 collisions, not a single one found.
Wow.
Across all those models, all the layers they checked, different prompts consistently produced different final hidden states. The theory held up perfectly in practice.
That's incredible confirmation. We said collisions should be on a measure 0 set. Were the hidden states even getting close to each other? Maybe near the limits of floating point precision.
That's another interesting finding. No, they weren't close. They measured the minimum distance between any pair of hidden states they compared. It always stayed orders of magnitude above the threshold they used to define a collision, which was 10 to 6.
Okay, so definitely distinct.
For example, in Llama 3.1 8B's final layer, the closest any two states got was still a distance of 0.62.
0.620 is a huge gap in high-dimensional space.
Yeah.
These representations aren't just different, they're robustly separated.
Exactly. And they also noted that the separation often increased as you went deeper into the model.
So the model isn't blurring distinctions, it might even be sharpening them.
In some cases, like GPT-2 small, the minimum distances grew larger in deeper layers. It reinforces the idea that information isn't being lost. The representations are becoming more distinct.
And finally, the practical test.
Yeah.
How well did SipIt actually reconstruct the text?
They tested on 100 prompts, each 20 tokens long. SipIt achieved 100% accuracy at the token level.
Perfect reconstruction.
Perfect reconstruction every single time. It recovered the exact input sequences.
And how does that compare to older methods?
The sources contrast this sharply with approximate methods, like one called hard prompts. In the same tests, hard prompts got 0.00% accuracy because it wasn't built on this guarantee of injectivity. It was trying to approximate. So yeah, this work really nails down injectivity as a core structural property of these decoder-only transformers. The hidden states truly do contain the full information about the input, and this holds up through training.
It's a fascinating result showing how much the architecture itself dictates these properties. The proof here is specifically for decoder-only language models. It does make you wonder, though, this lossless property, this injectivity, could it apply to other complex architectures, maybe multimodal models dealing with images or music? Or is extending the analysis there still a significant open question for the field?